Hi, my name is Rebecca Tyree, and today we are going to learn a little bit about blockchain technology. In particular, we're going to be talking about Merkle Trees, which are the backbone to this new and exciting technology that we have today. So the first question is, what is a blockchain? Does anyone know the answer?
Yeah, that's like Bitcoin tracking.
Yeah, it is used for Bitcoin tracking. It was actually originally devised to enable Bitcoin functionality by Satoshi Nakamoto. What's special about blockchains, though, is they don't just store Bitcoin values. They actually distribute this information securely, right? They don't allow the value of Bitcoins to be changed. I mean, it would be great if you got a Bitcoin that was worth like $1 and then you could just change it to $1 million. But we use this implementation, right, of blocks in a tree of unique hashes. Now, I know that's a lot of big words, but this kind of tree, it's a binary search tree combined with a hash table, and it's called a Merkle tree, all right? Now, blockchain technology is used in a lot of things. As you said before, Bitcoin is one of them. Google Docs is also another example. Merkle trees can be used for secure and real-time file sharing. So the same updates are shared with everyone at the exact same time. And overall, it is used for what we call decentralized web activity, which means that we don't have to have the information stored in any one particular place, because the information is stored in this Merkle tree and constantly being revalidated and updated in real time. So blockchain technology enables us to do a lot of really cool things. Which brings us to the question, what is a Merkle tree? Now, that's something I mentioned in the last slide. And I mentioned that it was a sort of a combination between a binary search tree and a hash table. Now, the reason I say this is because what a Merkle tree is a binary search tree that at the base level, at its leaf level, has unique data, and then every other node in the tree only contains a hash of that data. Right, the top singular hash now is called the Merkle root. And this is important because you can take any number of unique data leaves, right? Any number of leaves, and hash them together progressively until you get one single hash that actually represents every single piece of data in your Merkle tree. And what's cool about Merkle roots is they can be used to verify that data has not been tampered with. Are there any questions about Merkle trees before we move on? All right, well that's great. I'm glad you're all keeping up. So now we're going to look at what a Merkle tree actually looks like, okay? So as you can see, here are our unique data blocks, right? These are what we call transactions if we're talking about Bitcoin. Then each file or data block, each block gets its own unique hash, right? And then what we do is we group these data blocks into pairs and hash them together, okay? So eventually, in this case we only have 4 data blocks, so it only takes us 4 levels to get to the top hash. So our top hash stores our Merkle root, which is our unique representation of all the data below our top hash. So this is a little bit about how Merkle trees work. We're going to talk about the function that we use for hashing, which is the SHA-256 function. Now the reason we use this is because this was the original function that was used for blockchain technology at the creation of Bitcoin. It was originally designed by the National Security Agency. It's collision resistant, which means that it's super hard to trace the Merkle root. If you're given the Merkle root, it's almost impossible to figure out what files or values are in the leaves, right? Because it's what we call a cryptographic hash function. And this is also the industry standard that we use to hash together transactions because of the Bitcoin example. Has anyone ever used SHA-256 in their programming before?
Yeah, you can get checksums, right?
Yes, that's absolutely right. A very good example. So bringing this all together, blockchain technology gives value to digital currency and enables secure file sharing. Merkle trees are hash trees filled with hashes that supply Merkle roots for comparisons to make sure that our technology is secure. And then we use the SHA-256, which is a collision-resistant hash function and the industry standard for creating blockchain technology. Are there any questions about this presentation before we move on?
Why we use SHA 256? Why not something more like a 512? Why not use something bigger?
So the reason we don't want to use something bigger is actually because Merkle roots can take a long time to process if they get really big. With Bitcoin, where there are, I don't know, potentially millions of values, right? We actually want the shorter hash function, particularly if we're typing in a dynamic language, to make sure that we keep our compiling and runtime down. Okay, so if there are no other questions, we will move on to looking at a little bit of code. So I'm going to go ahead and run this program real quick, and what you can see is the 13 originally generated random hashes of the data and the Merkle root that has been generated by the hashing together of that data. The first thing we have to do when we're creating our Merkle tree, aside from importing our necessary libraries, is to create our Merkle tree class itself. Much like binary search trees, Merkle trees are very hard to implement without using classes and without using recursion, okay? So our first function is going to find our Merkle root. So in this function, we're going to create our blocks. These are going to hold our block chains. We're going to check that our file hashes exist, because if we don't have any hashes in this program, we don't have anything to hash together to get our Merkle root, which is definitely a problem. So we want to make sure that we have data and that we have a place to put it. Then what we're going to do, we're going to go ahead and sort those hashes in a for loop and append them to our blocks, all right? Now, in Merkle trees, you want to make sure that you have an even number of blocks. Because we're putting them into pairs and hashing those pairs together, we need this while loop that says while length divided by 2 has a remainder, right? That's what that percent sign means. Then what we want to do is we want to extend our blockchain. We want to add an empty block onto the end, all right? And then we want to update the length of our blocks. Then what we're going to do, we're going to create a secondary list for our hashes to go. All right, so this secondary list is going to hold the hashes of our hashes. Right? So as we go up the Merkle tree, we are progressively hashing hashes together to create new hashes until we get our Merkle root. So our secondary class is going to hold our new hashes until we can update them as part of our Merkle tree. So in this for loop is where we're using our hash SHA-256 function. All right? This is where we actually are going to end up hashing our data together, is in this for loop. We want to make sure that we're hashing together pairs. That's why we have blocks x colon x plus 2. So this declaration of the for loop really just allows us to keep our Merkle hashes in pairs until we can hash them together and get down to one hash, which will be our Merkle root. Then we want to call our recursive solution, okay? So our stop case is going to be if the length of secondary is 1. If the length of our secondary list is 1, what that means is that we've found our Merkle root. We have found our overarching hash that is going to represent all of our data. So we definitely want to stop our recursion and go ahead and return that hash. Now I'm returning it in this program only up to 64 bits just to make it a bit more readable. Else, the length of secondary is more than 1, right? Because we checked that we had file hashes before, so secondary must be filled. So if secondary is more than 1 block long, what we want to do is call this function recursively and give it secondary, because now secondary is the one that we're going to be hashing, right? Secondary now becomes our original argument of file hashes. Now you could take this Merkle root and compare it to another Merkle root from the same data to see if the data has been altered or not. Again, that is how it is implemented in technologies such as blockchain and Google Docs, by constantly validating that we are looking at the same consistent data.
So that's a brief introduction to Merkle Trees. I hope you guys learned something, and I hope I can teach you more in the future.